Okay, so this is the third video in 1-3, the part 2 of 1-3 compounds discussion. And we had just talked about the naming of polyatomic ions, the basic ones. Now, to make matters worse, there are multiple versions of each of the above polyatomic ions, meaning that fewer or greater numbers of oxygens are present. And we're going to change the names in a predictable fashion when we have this situation here. Okay, we're going to change the name in a predictable fashion. And so if we have one less oxygen, so for example, if we had the nitrate ion, which was NO3, if we take away one oxygen, it would be NO2, and we're going to have ITE on the ending of that instead of ATE. So if I have sulfate, which would be SO4, if I take away one oxygen there, now we have sulfite. If I had chlorate, which was ClO3, if I take away one, I'll have chlorite, and the same with bromite or iodite. If I take away two oxygens, and I'm only going to do this with the central atoms that are in column 7, okay, I'm only going to be able to take away two in that group. So the ClO3, the chlorate, the BrO3, the bromate, the IO3, the iodate. If I take away two oxygens from that, I'm also going to add hypo in addition to ite. So it was chlorite before, if I just took away one. Now if I take away two, it's going to be hypochlorite. And the word hypo helps us out here because that means less than or lower than. So that's one less than the two oxygens, right? So it's one less than the chlorite, so it's hypochlorite. It's one less than the bromite, so it's the hypobromite. And as you might imagine, we might also be able to add another oxygen. So if I'm ClO3, that's chlorate. Okay, if I'm ClO3, that's chlorate. But if I add one additional oxygen for ClO4, we add PER, perchlorate. Or if I'm BrO4, I add the PER, and that's perbromate. So this is how these might change. So I've got this big group of polyatomic ions that are made of non-oxygen central atoms surrounded by varying numbers of oxygens, and the main ones of these, the most common forms, are going to be the ATE form, and this is the list of the ATE forms. Then if I have some that have less than one less oxygen, I'm going to have the ITE forms. If I have two less oxygens, I have the hypo-ITE form. And if I have one more oxygen, I have the per-ATE forms. Okay? Now, there are a few ions that don't follow this pattern that we need to know about. And there are going to be 5 of these: the acetate ion, the ammonium ion, the cyanide ion, the hydroxide ion, and the peroxide ion. I know this looks like an oxygen atom, but there are circumstances where I have O2, the group of two oxygen atoms, that the whole group actually has a -2 charge on it. Okay, we won't use that very often because it's a little confusing. But these are a few polyatomic ions I need to know that do not follow this pattern, this central non-oxygen and then surrounding oxygen pattern. Excuse me. Okay. Now, one thing to be aware of here is that there's only one of these polyatomic ions that's positively charged. Now, we're not going to go into the chemistry of how we get these polyatomic ions in any detailed way. The vast majority of these are obviously negatively charged, and there's only one of them, the ammonium ion, that's positively charged, and that'll be helpful or useful to us, useful knowledge to us when we talk about naming. So later in the course, we'll learn a little bit about how these come about. For now, just know they exist, and if I want you to be aware of specific ones, I'll give you the name and the formula and the charge if you're not an honor student. Okay, now the third type of ion that we have to deal with comes from the metals in the transition elements of the periodic table. Okay, if I go back to my periodic table, that's this group of elements right here, right? This group of elements. These are the transition elements, okay, because they're in the transition between the first two columns and the last six columns. So they transition from the first to the last six. That's how to look at that. And we don't talk much about them because the way that they do things is not nearly as consistent. There are a lot more rules, and we're only going to need to know a few of those. But there are a lot more ways that these elements are complex, and so we have to treat them separately. So their atomic structure is more complicated than what we've learned for the first three rows. The way that we determine and where their valence electrons are also differs slightly. We've learned. We'll learn more about how to tell how many valence electrons they have and how many they'll give up at a later time. For now, what I want you to know is that depending on the circumstances, these metals may have more than one number of electrons that they might give up. Okay, and so for example, if I go to the periodic table and I look at vanadium, and the number here at the top of the does have something to do with the number of valence electrons that are available, but in contrast to the A columns, where I can only give up one electron in column 1. I can only give up 2 electrons in column 2, 3 electrons in column 3, 4 in column 4, and so on. In these metals, and by the way, remember, all of these are metals. There are no non-metals here. All of these are metals, as well as these 14 columns of metals down here as well. All of these are metals, and so they will always have a positive ion. They won't ever have negative. But if I look at vanadium, it's in column 5b, and this might suggest that I have 5 valence electrons and that I can give up 5 valence electrons. But in some circumstances, if I'm vanadium, I might just give up 4 electrons. In some circumstances, if I'm vanadium, I might just give up 3 electrons or 2. It won't ever be 1, but I could give up 2, 3, 4, or 5 electrons, and I would have different charges then based on how many electrons I gave up. If I gave up 5, I'd have plus 5 charge. If I gave up 4, I'd have a plus 4 charge. If I gave up 3, I'd have a plus 3 charge. Okay, so this all seems very confusing to us. And the easiest way at this point for us to know for sure will be to refer to a transition metal table. And this will show us the most common numbers of valence electrons that any of these will give up. Okay, so unless I say otherwise, we will use the most common number in whatever we're doing. If I go here and look, scandium will always be a plus 3, but titanium usually will be a plus 4, but it might be a plus 3. It might just give up 3 electrons. Vanadium will usually give up 5, but it might just give up 4. It might just give up 3. It might just give up 2. Chromium, it's in column 6b, so it can give up 6 electrons, but usually it only gives up 3 electrons. It can give up 6 or it can give up 2. Manganese, column 7b, usually though it will give up 4 electrons, although it can give up 7 electrons. So you will be limited to using these numbers in this first row here, this first column, as the numbers that you use when you talk about ionizing. The number of electrons that it gives up, or the number of valence electrons that we're going to talk about. Okay, these will be the numbers that we use, unless I say differently. Okay, I didn't realize it, but the program I'm using is going to limit time here to 10 minutes for this particular edition. So we're going to have to stop it right there, and we'll continue from there in the video, which should be the last video for this part. Okay, so go ahead and go to the next video now.